So sorry, everybody that's not here. I forgot to hit record. I'm gonna show them the page so they can hit pause and copy it. This is the same thing from last week. And then everything else is just filling in. So if you have any questions on it, just let me know. There's that part. I'm sorry. And then this back page is just filling in. It's just how rhyme and sums. It's just the proof of a rhyme and sum and why it is what it is. But once we do them, you're gonna be like, hey, it's not as bad as it looks. All right, and so then we're down to here. As shown in the figure on page 303, for any positive value of n, the norm of the partition delta sub n is 1/2. So letting n approach infinity does not force delta to approach 0. In a regular partition, however, the statements that delta goes to 0 and n goes to infinity are equivalent. Very good. All right, definite integrals. To define a definite integral, consider the limits. The limit as delta approaches 0. From 1 to n, f of ci delta xi equals L. Got to remember back when we were doing limits a long time ago, there was the one with definition of a limit. This is going to come in right here. But again, it's nothing, it's just kind of relating it back. It's not really anything that you're going to do. To say that this limit exists means that there exists a real number L such that for each epsilon less than 0, there exists a delta greater than 0. Oh, greater than. But they're both greater than. I was looking ahead. I'll tell you the next one is less than. Such that for every partition of delta less than the other one, it follows that. So this would come from like that chapter 1, 2 that we did before. The limit minus the summation from 1 to n of SCI delta xi is less than epsilon, regardless of the choice of ci in the ith subinterval of each partition delta. You're not going to work with that right now at all. And I say right now because I don't know if you ever will or won't. I don't know. Just in this section, you will not. So the definition of a definite integral. If f is defined on the closed interval a to b, and the limit should say and, the limit of the Riemann sums over partitions delta, the limit as that delta approaches 0 of 1 to n FCI delta xi. If that exists, then f is said to be integrable on a to b, and the limit is denoted by. We write the same exact thing that we just wrote, and then there's going to be an equal part to the end. So the limit as that delta approaches 0 of the sum from 1 to n of FCI delta xi is going to be equal to the integration from A to B. So that's that's what we're doing today. Instead of having the interval written out for us, like from the interval A to B, you're going to have it on the integration symbol of f of x dx. The limit is called the definite integral. Of f from A to B. The number A is the lower limit of integration, and the number B is the upper limit of integration. It is not a coincidence that the notation for definite integrals is similar to that used for the indefinite integrals. It is important to see that definite integrals and indefinite integrals are different concepts. A definite integral is a number, whereas indefinite integrals is a family of functions. So when we integrated and we got plus C, that's the family. When we get an actual number, that's your definite. Okay, so indefinite has plus C, everything else has real. So continuity implies integrability. If a function f is continuous on the closed interval AB, then f is integrable on A to B. That is, you can integrate from A to B f of x dx. And that exists. All right, so now it's going to look like this, and it's a lot easier than looking at it any other way. Pretty sure there's an easier way to do this, but you've already done it. Okay, so this is nothing new. Okay, so we're going to start with delta x. How did we get delta x before? So remember, this goes from A to B. So our B is 1 minus -2 over n, which gives us 3 over n. How did we get CI? Same formula. How do we get CI? Try A plus I delta x. What was our A? -2 plus I, or delta x, was 3 over n. And when we reduce that, we get -2 plus 3i over n. You do the same thing, still finding the limit. We're doing the limit as n approaches infinity with the summation from 1 to n. I'm gonna write this up here just so you can remember FCI delta X. So that means plug our CI into our function. So what is our function? 2x. So we're going to plug in 2 times -2 plus 3i over n. And then we're going to multiply it by delta x, which was 3 over n. All right, so from here, it's all reduction and summations. I'm going to multiply this 2 times 3 is 6 over n, and I need to pull that out. So we're going to pull out our constant, just like always. And we're left with a summation of -2 plus 3i over n. Which is going to give us 6 over n. We're going to split our summation up of -2. Plus, what can I do to this 3i over n? What do I need to do before I do the summation? Take out the 3 over n, so I'm only doing the summation of I. Let's go again. 6 over n. What's the summation of -2? -2. Don't forget, we add a power. Everybody remember that? Plus 3 over n times, what's our summation of I? And now we're just going to simplify and then take the limit. So we're going to keep simplifying. What can I do? I'm going to take out this n. I'm going to go ahead and distribute. So I have 6 over n. Leave that one alone for a minute. -2n plus 3n over 2 plus 3 over 2. I'm going to distribute my 6n in. So -12n over n plus 6 times 3 is 18n over 2n plus 6 times 3 is 18 over 2n. I'm going to reduce that. And don't forget that I have to take the limit. So the limit is n approaches infinity of, what's the first one give you when you reduce it? -12. What's the second one give you? And the other one? 9 over n. What's the limit of -12? The limit of 9? The limit of 9 over n, which gives me -3. That's it. So it's the exact same thing. That just put BA on your interval on your integral. That's it. So the same exact thing. Definite integrals can be positive, negative, or 0. For a definite integral to be interpreted as an area, the function f must be continuous and non-negative. We've already talked about that. On A to B. Again, remember finding that integration and finding that number at the end is going to give you the area of the region. So if f is continuous and non-negative on the closed interval a to b, then the area of the region bounded by the graph of f, the x-axis and the vertical lines x equals a and x equals b is the area equals a to b of f of x dx. We've already wrote the area formula as the integration of f ci delta x, blah, blah, whatever, the limit. So this is the same thing. Okay. At this minute, you can evaluate a definite integral in, should say, two ways. Sorry, you can use the limit definition, which is what we just did. Or you can check to see whether the definite integral represents the area of a common geometric region, such as a rectangle, triangle, or semicircle. Sure. So very good. Sketch the region corresponding to each definite integral. We can do this on our paper really quick. I didn't add any graphs because you really don't need them. Then evaluate each integral using a geometric formula. So you'll see what it means in just a minute. So if I draw a coordinate plane for this one, how do I graph 4? What kind of straight line? Where does it go? How do I graph it? It's horizontal at 4. So this would be 4. It's a horizontal line. The 1 to 3 tells you where to bound it on the x-axis. So we're going to bound it at 1. And we're going to bound it by 3. What did that make? What kind of figure did that make? A square or a rectangle depends on what our measurements are, right? Square or rectangle. All right. So we don't need to use the integration. We can just do length times width. So think about this rectangle. What is your length from 1 to 3? What is your width or your height? Which is? That's it. So you don't always have to use integration, depends on what you have. Now, anytime you have a curve, you're going to. So that's the difference. All right, so let's graph this. How do I graph x plus 2? Where do I start? How do I move? Up 1 over 1, right? So it looks like this. And it's bound from 0 to 3. So I stopped at 3. What kind of figure do I have in there? Come on, guys. You can actually do this a couple different ways. You could even split this up into 2 figures because you don't know what this figure is. The trapezoid. Are we good with that? Trapezoids? Yeah. So to find the area of a trapezoid, it's 1/2 base 1 plus base 2 times height. Now, if you didn't know trapezoid, you could split it into rectangle, square, and a triangle. Okay. So it depends on what it is. So quadrilateral triangle. All right. 1/2. Your bases are the ones that are not diagonal. So the left or the top and the bottom on these are not our bases. It's going to be the left and the right. So you need 2 perfect lines. So how tall was this line? How tall is this one? Yeah, 5. It's 3 plus 2, right? So sorry. And then what's our height? So basically the width would be what? From 0 to 3. I think I did to 2, sorry. I meant to do to 3. Put that in your calculator and you're gonna get 21/2. If you give me the decimal, that's fine as well. Too. Yeah. All right, think about this one. What is this gonna give you? Use your calculator, graph it, tell me what it is. What? Okay, so we know it's gonna be curved because it's got the X squared. Specifically what type? Thank you, Bryant. I appreciate that. A couple of you are putting it in. I appreciate that. Oh.
Well, I don't know how to cut this. It's a parabola.
No, it's not.
It's whatever.
How do y'all not know your shapes?
It's been a while.
It's a.
Thank you. A half circle or a semicircle. Y'all are struggling. Y'all are struggling.
That's a house.
Circle is basic. Circle is basic. This is half a circle. It's okay. Same thing. Half circle, semicircle. That stretches from -2 to 2 and it goes all the way up to 2.
I was expecting some wild shape when I hit dry.
No.
No.
Yeah, it's a tough one for you guys. So how do we find the area of a circle? Pi r squared. Well, we have a half a circle, so we're going to do half pi r squared. Half pi. What's our radius? 2. Very good. I thought that would be a struggle for a minute. I was worried. 2 squared is 4. Half of 4 is. Now we're going to leave it in terms of pi, so we don't have to have a decimal. That's it. Right. So the variable of integration in a definite integral is sometimes called a dummy variable. Easy. I knew all the jokes were going to come because it can be replaced by any other variable without changing the value of the integral. For instance, the definite integrals from 0 to 3 of x plus 2 dx. And the integration from 0 to 3 of t plus 2 dt are the same. So it doesn't matter what variable you use, it's all the same. The definition of the definite integral of f on the interval a to b specifies that a is less than b. However, it's convenient to extend the definition to cover the cases for which a is equal to b or a is greater than b. Geometrically, the next 2 definitions seem reasonable. For instance, it makes sense to define the area of a region of 0 width and finite heights. That means it could be any height to be 0. Okay. Definition of 2 special definite integrals. If f is defined at x equals a, then if our upper and our lower are the same, then our area is going to be 0. If we switch them around, instead of going a as our lower and we put a as our upper, then all that does is it makes the area negative. That's a b. So you do it the same way. It's just going to have a negative out front. Better hurry up. Missing the good stuff.
I thought this was the good stuff, that's why I was waiting. That's all the little examples.
All right, evaluate each definite integral. So from pi to pi of sine x. If it's going from the same pi to pi. We have equal bounds. And remember anyway, that sine pi is equal to 0. So this one is going to equal 0 no matter what. Again, anytime it goes A to A, it's going to be 0. What's different about B is that your lower limit is actually larger than your upper limit. So you would change it by pulling out the negative. And then remember, we did this x plus 2 on the last page, 0 to 3. And we got 21 over 2, but because they switched the boundaries, we're going to get negative 21 over 2. Previous example. Okay, where we did the regular like trapezoidal area. All right. If f is integrable on the 3 closed intervals determined by a, b, and c, then the integration from a to b of f of x dx is the same as the integration of a to c of f of x dx, which is the same as c to b of fx dx. All right. So we have the integration from -1 to 1 of the absolute value of x dx. And that absolute value of x we can split into so that's this part up here at the top, -1 to 0. So what did I do? What did I do right there? I'm going to split that interval in half. Does everybody understand that? Okay, you told me split it in half. Remember that. The reason I'm going to do that is because what happens with absolute value? There's a negative and a positive. A regular absolute value is positive, but the number that I plug in could be positive or negative. So if I wanted, for example, the absolute value of x equals 3, x could be 3 or x could be -3 when I plug it into the absolute value bar. Does everybody understand that? So what we're doing is kind of bounding that negative versus the positive. So these are going to be your negative values. And then I'm going to go 0 to 1 of my positive values. We can do our formulas. We can graph this negative x and do our geometric formulas that we just did. I'm just going to go ahead and tell you that this area is 1/2. How you said we were splitting it in half. The other area is also going to be 1/2, which adds to a total area of 1. Because the definite integral is defined as the limit of a sum, it inherits the properties of summation. And again, where did I get the 1/2 and the 1/2? That would be me drawing. We start at 0, we go down 1 over 1, down 1 over 1, and then you're making that shape. Okay, and finding that area of that shape. But to save you some time, I just went ahead and put that area. All right, if f and g are integrable on a and b and k is a constant, then the functions kf and f plus or minus g are integrable on a and b. So you've seen this before. This is nothing new. Again, we're just putting that A and the B on that integration sign of K f of x dx. What do we do with the constant? What have we always been doing with the constant? Pull it out. So that's what that one says. Pull out the constant. We do our integration from A to B of f of x plus or minus g of x dx. So this is like we had that -2 plus or minus 3 over n. We would split them up. So we do the integration from A to B of your first function, dx, whatever it is, add or subtract the integration of your second function, dx. So nothing new. This last example might be the easiest problem on the whole page. I think it is. How about that? It's pretty simple. All right, is everybody good with all this? Almost. Good now, everybody? All right. Evaluation of a definite integral, evaluate the integration from 1 to 3 of -x squared plus 4x minus 3 d of x using the following values. So what's the difference in these two? It's not hard. Remember, I told you it's easy. Don't overthink it. What's different? One's negative. So what can we do with that negative? We can pull it out. Okay, so we're gonna talk about that. What's different between this? There's a 4. What do we do with our constant? Pull it out. So then we have a -3. Remember when we do our integration of -3, we're gonna leave that 3, and then what do we do? We're just gonna add that n in. So watch this, just be careful. So the integration from 3 to 1 of -x squared plus 4x minus 3 dx. We're gonna split it up into the negative integration of 1 to 3 of x squared. You said I can take the 4 out, integration 1 to 3 of x, minus, if I pull the 3 out, the only thing I have here is that dx, okay? So it's just like having a 1. So what did they say the integration from 1 to 3 of x squared was? They gave it to you. The integration from 1 to 3 of x squared of dx is 26 over 3. So we pulled out a negative, so we're going to put that in front. We pulled out a 4. What's the integration from 1 to 3 of the x that they gave you? 4. Then we pulled out a -3. What was the integration from 1 to 3 of dx? 2. Then you just put it in your calculator. Don't overthink it. Gives you 4 things. Don't overthink it. This is what you'll be doing soon. Okay. All right. If f and g are continuous, no more examples, just writing. On the closed interval a to b, and 0 is less than or equal to f of x, less than or equal to g of x. For a less than or equal to x, less than or equal to b, then the following properties are true. First, the area of the region bounded by the graph of f and the x-axis between a and b, which we already know, must be non-negative. You guys understand that if it's negative, you can't have a negative area. Second, this area must be less than or equal to the area of the region bounded by the graph of G and the x-axis between A and B. These two properties are generalized in theorem 5.8. So if f is integrable and non-negative on the closed interval a to b, then 0 is less than or equal to the integration from a to b of f of x dx. If the f and g are integrable on the closed interval a to b and f of x is less than or equal to g of x for every x in a and b, then the integration from a to b of f of x dx is less than or equal to the integration from a to b of g of x dx. So these just put in that whole writing. That's what it looks like. Any questions? So did we really do anything different? No. So it should be the exact same thing that you've been doing. Here's your homework. Page 309. 18, 22, 25, 42, 46, 53. Okay. No, Mackenzie, I will not move my paper. Is that good enough? Or you need more? Okay. Sometimes it takes me a long time, sometimes it's really quick. Just depends on my mindset. All right, let's stop.